Happy Rotary Monday, everyone. As I get through the first couple of weeks, I get good feedback on the experience that Rotarians have while I'm standing up here. And one of them was to give the bell a little more gusto. And so hopefully, what's that? I can't break it. So gusto it was. It is so wonderful to see all of you here today. Please join me in the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. And as we've started to do, please join me in the four-way test of the things we think, say, or do. First, is it the truth? Second, is it fair to all concerned? Third, will it build goodwill and better friendships? Fourth, will it be beneficial to all concerned? I'd now like to invite Joel Sylvester up to the stage for our invocation.
Good afternoon, fellow Rotarians. I have strict instructions from Dean Johnson to keep it short, so I will do that. I would invite you to pray with me. Creator and sustainer of all that is or will ever be, accept our thanks for this day and all its blessings. We ask that you guide and direct our club, its leaders, and our actions. Grant that each of us may feel our responsibility to Rotary, to our community, to our country, and indeed all countries and peoples. Please bless our fellowship today, bless those that have traveled to join us today, and bless us all in our service. Amen.
We have a number of guests today, so in interest of time, we certainly want to celebrate our guests. I would like to invite each of our guests to stand along with the person or persons who invited you. We would like to give you a warm Rotary welcome. Thank you so very much for being here. And I will take a moment of personal privilege. I brought a guest today, and her name is Maddie Peterson, and we are having a wonderful Monday Mother-Daughter Day today. So, Maddie, thanks for coming. Let's get down to Rotary business. You can see in front of you here that one of our priorities for this year is to provide our members a more robust Rotary experience outside of our Monday meetings, if that's what you as a Rotarian would desire. That is a priority for this Rotary year. We have opened up committees and volunteer opportunities that come with those committees. We've essentially had to pause those the last 2 years because of our favorite word, COVID. So we have now resurrected past committees, created a couple of new committees, and I'd like to recognize and thank the Rotarians who have agreed to chair these committees. If you are here, would you please stand? We have our Branding Communications Committee, Eric Ellefson. Eric is also chairing our Program Committee. We have a new committee called Member Connections. If you recall, we have had 100 new members join our club in the last 2 years. Our Member Connections Committee, chaired by Matt Dittmanson, is an effort to really find a way to engage all those new members into the Rotary mission and the things that we do here. So thank you, Matt, for that. Joel Sylvester, who we just saw, he is keeping busy with Rotary, chairing our Membership Recruitment Committee. Brian Mulder is chairing a committee we call Monday Logistics. So all of the things that happen behind the scenes at each of our meetings, Brian will be spearheading. And if Brian's here, I sure want to thank him. From there, we have our Engagement Committee. We've given it a little bit of a fun name, More Than Mondays Committee. Jen Hazing has been at the helm of this committee for a number of years and has agreed to continue in that role moving into the next year. So I want to thank Jen, though I don't know if she is with us today. From there, we are also engaging a committee. We do a lot of these elements, but we've never really put them into one place, at least not for the last few years. And so we have a Rotary International Committee. There are so many elements to this committee. We actually have 2 chairs, Kayla Etrium and Dave Eastland have agreed to chair that committee together, and we've got them, they're covering the whole room. We got them side by side here. And certainly last but not least, Sue 52, we will continue all of the great work, taking it to the next level, will be Eric Erickson. So Eric, thank you for stepping into that role today as well. If you are at all interested in learning more about these committees, or you see yourself getting involved in a committee capacity, these chairs are putting their people power together here in the next 30 days. I think the most efficient way to share your interest would be to go through Angie, and she'll take all those pieces and make sure they move in the direction they need to go. You're also welcome to reach out to me or the committee chairs themselves, whichever makes the most sense to you. One of those 100 new members is being inducted today. I'd like to invite Stephen Williamson to introduce our newest member. And Steve, thank you for all of the new members you've brought into the Rotary fold this past year.
Good afternoon, Chair, fellow Rotarians. It is my honor and privilege to introduce to you Jackie Kramer. Jackie Kramer is Associate Dean of Curriculum Instruction of the Nursing Programs at Southeast Technical College. It is one of our largest programs. It is also one of our most successful, and she is a big reason for that success. We probably graduate, give or take, about 250 LPN and RN nurses on an annual basis. Jackie is wonderful to work with. She is wicked smart, and she's very, very motivated. She's originally from Sioux Rapids, Iowa. She has her bachelor's degree from the University of Sioux Falls. She has her master's from Indiana Wesleyan. She has a husband and a child. Everybody, Jackie Kramer.
Good afternoon. Like Stephen said, my name is Jacqueline Kramer, Associate Dean of Nursing, so directly oversee the nursing programs at Southeast Tech. I am a first-generation college student, so I have been a nurse since 2002. Started at a community college and then kind of worked my way up through my education. Been at Southeast Tech since 2011, so started as faculty and now in this role. So it's been quite the ride, and I've enjoyed every piece of education. So being a first-generation college student and going through community colleges and then also on through USF and Indiana Wesleyan, education has become a passion of mine, particularly two-year education and the student population we serve. So I'm excited to be a part of the Rotary. I think the mission and vision of the Rotary really fits me personally and professionally. So I'm excited to see what it brings. So thank you, everyone.
Jacqueline, thank you so much for joining Downtown Rotary. I look forward to getting to know you over these next weeks and months. Now, on to today's program. Our presenter, Bill Ochs, has 40 years of experience in the aerospace industry. He has worked in both private industry and for NASA. He began his career in 1979 developing the flight software for the Hubble Space Telescope system. Bill also has worked on the Solar Radiation and Climate Expert, SORCE, and the Landsat 8 projects. Bill is the project manager for the James Webb Space Telescope at NASA's Goddard Space Flight Center. Bill will share an overview of the Webb Telescope, engineering challenges, the Webb Telescope launch, verifying Webb in space, and early science observations. Bill has been the recipient of the NASA Exceptional Achievement Medal, the Spaceflight Awareness Honoree Award, various NASA Group Awards, NASA Honor Award for Outstanding Leadership Medal, and most recently, the Robert H. Goddard Award for Outstanding Leadership. Please, the warmest Rotary welcome to Bill Ochs.
Thank you all. So what I'm going to do today is kind of give you guys a little introduction into Webb. We'll talk about Webb itself, what makes it special, what makes it different from Hubble, how big it is and the size it is. Talk about a couple of our engineering challenges, kind of give you an oversight at the launch site. We're kind of unique because we're an international mission. We didn't launch out of Kennedy. We launched out of Kourou in French Guiana. And then finally, I'll wrap up with some of the science images that were released a couple of weeks ago and talk about that a little bit as far as an engineer can talk about science, which is always a tricky thing. So let's see how this works. Okay, so what I'm going to start with, we have a mission trailer. The mission trailer we did prior to launch. It's a great intro into Webb. I like to play that at the beginning of any presentation I give, and then we'll pick up from there.
We have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth. If we crave some cosmic purpose, then let us find ourselves a worthy goal.
Chart. Okay, so like I said, I'm going to kind of give you an overview of Webb. I have no charts in front of me, so I'm going to kind of turn to the side once in a while. I can't see the screen over there, so I'm not ignoring all of you, but I'm going to turn this way so I remember what chart I have up here. So there are some major differences about us and the Hubble telescope, but our goals and the science that we've determined back in 1995 to do with the Webb telescope has driven our requirements for this mission and the hardware that we built. So there's couple of big things that stand out about us. One, we're a lot bigger than Hubble. If you look at the Hubble telescope and compare it in some sizes, a Hubble is about the size of a school bus. We're about the size of a 737. We have about 6.5 times the light gathering power of Hubble. That's what's key to any telescope is collecting that light, the light bucket, and collecting photons. We also look at a different part of the light spectrum than what Hubble looks at. Hubble looks at the visible light that we normally see with a little bit of infrared and a little bit of UV. We are purely an infrared telescope, and we look at a couple different spectrums within that infrared range. That is driven by some of our science requirements. We'll talk later about the type of science that we do, but we want to be able to look back to the very beginnings of the universe. I'll show some examples of that later, going back up to 13.6 billion years ago. To do that, as visible light travels through the universe, the light waves start to elongate. And as they elongate and stretch, they shift from visible to the infrared. So that's why it's important to look at the infrared part of the light spectrum. That then drove other requirements in the construction and design of our satellite. And we'll kind of talk about some of that as we go through my presentation. So let's talk about the observatory a little bit. As I mentioned, we are a very large observatory, like I said, the size of a 737. This kind of just gives you 48 feet across. Height-wise, we're about the size of a 3-story building. We have our primary mirror. Our primary mirror is about 22 feet across, or 20.5 feet, somewhere right around there. We're much different than the Hubble mirror, not just size-wise. Hubble was able to manufacture one single mirror. We had to fold up to fit inside a rocket. So we actually built a segmented mirror. So our primary mirror is made of 18 individual segments. Each segment is about the size of a coffee table. On the back of each segment, there are 6 motors that allow us to move that mirror so we can align all those mirrors to each other to form one perfect telescope. We'll talk some more about that as we go through what we did on orbit. We have a sun shield. The sun shield, so if you're going to look at the infrared part of the spectrum, your telescope and the cameras and spectrographs that we use have to be really cold. Our telescope itself sits about 40 degrees Kelvin. We have one of our instruments that have detectors that are kept at 6.7 degrees Kelvin, which is about It's only 6.7 degrees above absolute zero, all molecules stop. To achieve the 40 degrees Kelvin, we built this big sun shield. It's about the size of a tennis court. Basically, it's a big sunshade. And it keeps, by keeping that shade on the telescope and on the instruments, it allows us to get as cold as we need to get. That 40 degrees Kelvin, I tend to talk like that, is about minus 385 degrees Fahrenheit, just to kind of put it in context. There's the size of our sun shield. And come on, there we go. We have 4 scientific instruments on the back of Webb. We are an international mission, so we have partnerships with folks who provided some of the hardware. 2 of our instruments were built over in Europe, 1 instrument built in Canada, 1 instrument built in the US. They're all housed on the back of the telescope. On the bottom, let me get the right pointer here. Sorry, I can't even point to that one over there. So on the bottom down here, we call it the Spacecraft Bus. That has all like the housekeeping type stuff, our electronics, solar panel, communications equipment, our thrusters, and so on are all controlled from down the very bottom, and that's the cold side of the bus, the hot side of the bus. So all this has to fit inside a rocket, which means you take this huge thing that was deployed, and it has to fold up like that to fit inside a rocket. We used to joke around, it's kind of like origami on steroids to be able to do this. I have a video later that shows how we unfold all this, and we talk a little bit about what we had to do in those first couple of weeks of the mission to get to the shape that we are. As I mentioned, we are an international mission. We have partnerships with the European Space Agency, the Canadian Space Agency. As I mentioned, the Europeans provided 2 of our instruments. They also provided the rocket. The Ariane 5 rocket is the most reliable rocket flying nowadays. It means we go to their launch site, which was in French Guiana and South America, which posed, as you can imagine, lots of logistical challenges, both to get our hardware down there and people down there. But overall, and then our folks from Canada built one of the instruments. Overall, we had participation from 29 US states and 14 countries to build the Webb telescope. Took about 20 years to build Webb, with about 20,000 people to build the telescope in the observatory. Some high-level comparisons besides just the size to Hubble. Even though we're a lot bigger than Hubble, we're about half the mass of Hubble. That was to allow us to get into the rocket and get us to our orbit, whereas Hubble is a low Earth orbiting satellite. We are about 1 million miles from Earth, so 4 times the distance to the moon. And we'll talk a little bit later about why that's important and why we went there. I already talked about the light gathering capability, and we also operate, obviously, at a much colder temperature, which I've already alluded to. So engineering challenges, we had lots. I could be up here for 4 hours talking about our engineering challenges. I'm going to talk at a high level about a couple, dealing probably the more obvious ones, which is our primary mirror and then the sun shield, and a little bit about how we integrated these things together. So Webb's primary mirror, as I mentioned before, it's a segmented mirror. It's made up of 18 segments. Each segment's about the size of a coffee table. They're made of a material called beryllium, which had never been done before. We chose beryllium because beryllium is very stiff, it's lightweight, and it's very stable over very cold temperatures. Doesn't change its shape much, which are very all important things to Webb. We started out with blocks of beryllium for each segment that were 550 pounds. After lightweighting and polishing, you ended up with a 46-pound mirror. To give you an idea of the type of polishing, the fine polishing that we did, if you took one of these segments, that's the size of a coffee table, blew it up to the size of the continental US, take your worst imperfections before you start polishing, make that the size of Mount Whitney, which is the highest mountain in the continental US at 14,500 feet. By the time we finished polishing, that mountain was now 2 inches high. That tells you the type of polishing that we went through over multiple iterations over many years to achieve the perfection that we have in these mirrors. It wasn't done just in one place, each mirror. Our friends at Northrop Grumman out in California were the observatory contractor. They subcontracted out to Ball Aerospace in Boulder, Colorado. They do the mirrors. But it wasn't just done there. It was done all across the country, and each mirror traveled 15,000 miles before it ever got mounted to its permanent structure. And And then you take this 46-pound mirror, and how do you put it onto the back part? We call the back plane, which is where it gets mounted on a telescope. I have some pictures in a minute, but we used 139,000 pounds of support equipment to actually mount a 46-pound mirror onto the back of a telescope. It had to be so precise. So here's some pictures. So up here in the top left, we use a robotic arm to mount each segment onto the back plane. We're in a clean room environment, so that's why folks have a bunny suit on to protect the hardware from contamination. You just can naturally off of our skin and clothes and so on. It's lowered in, and then the technicians mounted it to the or adhered it to the back plane. This is when it was done with all the covers on. And we then took the covers off. We use these things called diving boards that the technicians would lift the cover and gently bring it off, and that was our finished mirror. So how do you test this thing? Everybody's familiar with issues that Hubble had when it first launched. We did not want those issues, obviously. So we did a test down at Johnson Space Center. We needed a very large chamber. There's a chamber down there that's 7 stories tall that was built for the Apollo era that we took and converted it into the world's largest cryogenic chamber. Cryogenic meaning it can get very, very cold. So this is a drawing of that chamber. And the pictures really don't do justice because we had to put a clean room in front of it, so you can never really see the whole chamber in scale to, let's say, a human being. Even this door is huge. It kind of does some justice here, but not quite enough justice. But this is us getting ready to go into the chamber itself as a fully deployed telescope. And then this is our inside that chamber. It took us many years to get to that point. We did a lot of testing early on just to test out the capability of the chamber. We came down there with a protoflight, make sure we could execute the test. And the test itself took 110 days with a good old Hurricane Harvey stuck right in the middle of it down in Houston. So that added another level of complexity to it. But when we got finished with that test, we knew ever before going into space that we had a perfect mirror that was going to perform the way it's been performing on orbit now. So next is our sun shield. So this is how we cool off the telescope and the science instruments. The sun shield itself, there we go. So, like I said, it's about the size of a tennis court. It's made of a material called Kapton. If you think of a mylar type balloon material, it's kind of similar to that. Each layer of Kapton is only the thickness of a human hair. Each layer is made up of 50 individual pieces that are thermally stitched together, and each layer has a unique shape. And you can see here, I like to, oh, oops, what happened? There we go. Oops, I gotta go back. Pointing, hold on. I'm getting ahead of myself here. Here we go. So, oops, one more. So down here, you can see, here's the temperature differential. On the hot side of the spacecraft, you have energy coming in from the sun and the earth. We're sitting at plus 185 degrees. By the time you get to the cold side of the spacecraft, just from the sun shield, you hit minus 385 degrees. The other way to look at it is you have 200,000 watts of solar energy hitting that hot spot, and what pops out the other side is 0.02 watts of solar energy. That's how efficient this the sun shield is. So now, how do you test this and know it works? Sun shield was too big to deploy in any kind of chamber, even the one down at Johnson. So we had to use mathematical models to determine its honor performance. So we determined to verify those mathematical models, we built a 1/3 scale, perfectly matching the sunshade design, put it into a chamber and ran it, put it through its paces, took those results, matched them to the models, and had to make adjustments to the models. But once we got everything to match, we knew we could predict its performance on orbit. So you can see this is the 1/3 scale model here. Now, the other issue is, or challenge, was you have to handle this thing on the ground. You have to deploy it. And then you got to fold it back up each time you deploy it. It's a very delicate operation. We had to train technicians to be able to do that. So we built a nice full-scale model that could be deployed. And every time we deployed it, they would practice then folding it back up. And it provided an outstanding learning opportunity. We learned everything on how better to deploy it, how to fold it back up. Technicians, nobody's perfect. Technicians will make mistakes. They might poke a little hole in it. We learned how to patch those things so that we knew what we were doing when we were going in, at least we thought we were, going in when we were building it. And we still learned some things then, but we tried everything out on this full-scale model. So these are some pictures of the sun shield. You can kind of get a sense of scale with that top left picture with somebody standing in the center, another one on the top right, and this is how we're folding on the bottom. You pick it up. I describe it as if you've ever been in a department store and you see somebody folding shirts, they have a folding board. Well, one of our engineers saw that and derived from that a way of folding the sun shield, essentially using folding boards to get it into its perfectly folded shape to get it to be able to store it for launch. So now the challenge is, how do you put this together? So we got these, I can't go through the whole process, so again, we'd be here forever. But you ended up in the end with two big pieces. At Goddard, you had the telescope been put together with the instruments integrated onto the back of it. Out at Northrop Grumman, we had the spacecraft, what I called the bus before, and then the two sun shield pallets holding the sun shield, and those two pieces had to be put together. That was done out at Northrop Grumman, and this next video shows you how we put it together and then the final deployment of the sun shield. So I'll let that run and then we'll talk some more. Okay, so now we're going to skip forward and talk about launching. As I mentioned before, there we go. The rocket was provided by the Europeans as part of our agreement with them. So their launch site has to be close to the equator. It's down in French Guiana in Kourou. To get there, we were so big, once we got inside of our shipping container, we could not fit in your largest transport plane like a C-5. In addition, if we even got down there between the airstrip and the launch site, there were 7 bridges that would not withstand the weight of Webb, along with all the associated hardware that goes with it, with the shipping container and so on. So we went by boat. We used the same ship that the Europeans used to ship rockets and their satellites down to French Guiana. It picked up the ship, our stuff at Navy SEAL Beach Weapons Station just south of Long Beach. I have a video on that showing us being loaded onto the ship, through the Panama Canal, and then over to French Guiana. Trip took about 16 days. Let's see. There we go. So this video shows us leaving a Navy SEAL Beach Weapons Station. It was a roll-on, roll-off ship, so we used a roll-on, roll-off barge that we got onto first, and then almost did like a K-turn to bring it up to the garage for the ship. In addition to the satellite itself, we had to bring the equipment down to support all our operations down there. We had 40 trailers, ranging from 20-foot trailers to 40-foot trailers, of equipment that we brought down to the launch site. We were down at the launch site for approximately 3 months. We had folks that sometimes stayed down. Some of our folks stayed there the whole 3 months. Some only came home for a week. We had a very dedicated team down there. At the peak of our number of folks we had down there, we had over 200 people at the launch site. And there we go. We had 4 of our folks on the ship to monitor all the environmental control systems. And it was a great trip. We had no rough seas. Their biggest disappointment was when it was our turn to go through the canal, it was that night, so they didn't really get a chance to see anything. Okay. So now we're going to talk about the launch. This video will take you through being in their vehicle assembly building, through the rollout to the pad and the launch itself. This is going up an elevator shot out of the window that takes you up the side of the rocket up to the top level where we integrated Webb onto the telescope, onto the rocket.
And we have engine start. And liftoff.
Décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
I stopped this video here because the next one I want to show you is actually the separation. This was the first time Arianespace had put cameras on their rocket. There we go. Yeah, there we go. So we see the actual separation of Webb from the rocket itself, and we get through a little bit of dead time, and then you'll actually see the solar array deploy. What you'll see first, you see some blue flashes on the bottom. To dampen the rates that the rocket might impart on the satellite, we fire our thrusters to get a nice gentle ride. They actually did a great job of dropping us off. We really didn't have to dampen the rates too much. As soon as those rates dropped below a certain level, the solar panel automatically deployed. And it was the only autonomous deployment we did out of the 40 plus deployments that we had to do to get to the shape that we're in. But as you watch this, the little pieces you saw floating away, that's actually just ice from inside the fairing. Nothing from the telescope pieces of the telescope weren't falling off or anything. At this point, control of the satellite now is turned over to the operations center, which is on the campus of Johns Hopkins in Baltimore at the Space Telescope Science Institute, about 25 miles north of where I work at Goddard Space Flight Center. I was trying to kill, hey, I did kill some time. And there is the solar panel coming out all by itself. The whole place went crazy when we saw that. Because now we knew we were going to be positive power. That's a big thing. All right, let's go. There we go. So when you get, and any satellite goes through this period, we have to commission a satellite just like you would commission a ship for the Navy. Our commissioning period was 6 months. We went a little bit longer than that. But the first part was the first 2.5 to 2.5 weeks. This is where we had to deploy and go through all the points. We had 40 deployments with 178 devices of 9 different design types that had to work. We had 155 motors. We had 600 pulley assemblies, 1,300 feet of cable, and I could just go on and on with the complexities that were involved. Any failure in that spot could have ruined the mission. It all worked perfectly. In fact, when you look at the top, there's a clock going off. When it hits the final deployment, we were within minutes of that. And this video was made probably 7-8 years ago. That's how precise and where we held to our timeline. The only issue we had actually occurred before this. So on the sun shield itself, there are some covers that roll back. They're covers that are protected during launch. When these roll back, they roll back and they fall into a notch. They rolled back, they got stuck right before the notch. We actually had seen this in testing on the ground. And when you saw the sun shield being pulled out by these mid-boom assemblies, we basically went ahead and made this thing go ahead and pull it out, and that just forced them right to drop into that notch. So we lost maybe a half a day. We just sat around and calmly talked about what we were doing. Yeah, I know. I read an interview last week from one, I won't mention names, but one of my guys, and he added so much drama to it. And I'm like, I don't know, I was there. There wasn't a lot of drama. It was sit down and just talk it through. And then we made the decision to move forward and start the process again. And keep going. Oh, am I good? Good. So what you see up here, the timeline across the top shows the whole commissioning timeline. So you start up by commissioning the spacecraft. We get through deployments. There's like a transition period. We have to start letting things cool off. That's what we did during that transition period. We then focused the telescope, and I'm going to talk a little bit about that in a minute. And then we had to commission each one of our science instruments, and that consisted of all the different science modes they had. There are, at an observatory level, there are 17 different science modes that we can do with Webb. To align these telescopes, so you essentially have 18 mirrors. You essentially have 18 telescopes when you start. So the image you see over here on the left, these little dots, these stars, are the same star, but they're all in the different 18 mirrors. So you find them at first. Like I mentioned, we have these motors on the back to be able to move the telescope. So then we begin the alignment process. We got to this next step here, where now it kind of looks like you're in each of the hexagonal shape of the telescope primary mirror itself. They're just not focused yet. Then once we finished focusing, this was the first image we released. A nice, perfectly focused star. What a lot of folks really focused on was, hey, that focused star is really cool, but all those other little dots behind here are all galaxies. And this is just with the first ever image we ever took, where we had it all focused. And we found, one of our engineers went through it. Oh, first we went, come on, advance. There we go. So that was a cropped image. Here's the full image. And then we took and he created a photo montage of over 250 galaxies, many of which we had never seen before because we were looking at things in the infrared spectrum. And this is just with the first image that we took. And it was done with the fine guidance sensor image, which helps us pointing. So it's not even one of our real science instruments to really get the depth that you'd want looking back through the universe. So, Webb science. We have 4 science themes. As we move forward, there's going to be more and more, because as you learn to use any tool, the more you use it, the more you learn, the more different things you can learn to do with it. So looking back at first light, we'll talk about that. So looking back to the very beginnings of the universe, how galaxies are formed, what happens when 2 galaxies merge together. We've already seen instances of that in some of our first science images. The birth of stars and planetary systems. And then finally, the part I think that's really cool is, oops, come on up. So looking at the foundations, looking for the basic elements of life as we know it, looking for things like oxygen, hydrogen, nitrogen, carbon, and so on. That can be done, and I'm going to explain another chart how we do that with Webb, but that's one of the things that we are out doing, and we've already looked at one exoplanet already and have found some pretty amazing stuff. The other thing we can do when you're looking at infrared, this is a nice Hubble picture. You got all this gas and stuff in there, but because we're looking really at heat, since we're looking at infrared, you can actually see through that. Hubble can do a little bit of near infrared, and so just with the near infrared, that's kind of what you get when you look with a Webb telescope. Like I mentioned, we can study other worlds. And the way we do that is, as a star passes in front of a planet passes in front of its sun, the brightness of that star will dip depending upon the size of the planet. And over the last probably 10 years, we've now discovered about 5,000 exoplanets. We're discovering more all the time. And we've determined the science enough, we can determine the mass of that planet, the size of it, how far it is from the sun. We now have what we call the Goldilocks planets. Those are the ones that are about the size of Earth, about the same distance from their sun as Earth is, about the same temperature, have probably the highest probability of having all those basic elements of life. So when we do that, we'll come back to that. I always forget, that's a couple of charts now, but I'll show you an example of what we did with Webb in the first month of operations. So this is the first image we released a couple of weeks ago. This is what we call a deep field image. Hubble has released deep field images in the past, but none has gone as deep as this. Their deepest image took about 2 weeks through exposures. This took Webb 2 hours. We did it multiple times, so you can stack with different filters on top of each other to give you more depth in what you see. But again, this is about a couple of hours with Webb. And what you see, which is really interesting, and you see these arcs in here. Sorry, I can't do it on the other screen, but you can see like these little things of light coming through. What that is, in the center, right around here, these stars that are stars that are in our Milky Way. Everything else are galaxies. You have a cluster of galaxies. Well, they are so massive and their gravitational field is so strong, they bend the light from objects behind it around the galaxies. So it's called a gravitational lens. It's something that Einstein had theorized and was proven by Hubble a long time ago. You can get everything from these thin arcs of light to you actually get mirrored images, which we've seen. And then sometimes it will distort the image, like you can see up here. Kind of if you turn your head on the side, it looks like that painting called The Scream. It kind of looks like that. If you go to webtelescope.org, you can view these images, and then there's one you can view a zoomable image, so you can zoom in. I highly encourage everybody to go play with it. There is so much cool stuff in these pictures. It is unbelievable. But this is the image where we've seen the deepest we've ever seen in our universe. So on this chart, what it shows, and I know it's hard to read, but you can see these online also, we are able to measure the redshift. And redshift means you can measure how far back you're looking. So in that image, the galaxy farthest away was 13.1 billion years ago. So we're looking at light from 13.1 billion years ago. We then put our spectrograph on there, and you can see some of the elements that we found coming from that galaxy. We found, I think that's oxygen, hydrogen, and neon, primarily coming from that one. So we're already starting to find those basic elements of life, looking even at galaxies. This is another image called Stefan's Quintet. I always tell folks, if you ever saw the movie It's a Wonderful Life, when the angels speak, there's a ground. What's behind the angel speaking is a ground-based image of this Stefan's Quintet. They're all not the same distance. The galaxy over here on the far left is about 46 million light years away. The rest of them are about 290 million light years away. The cool part is these two galaxies you can see as two bright dots down here are merging. They're colliding with each other. And the violence of that is creating shock waves, which you can kind of see in this red area up here. You're seeing gases up there that are around 1 million degrees Fahrenheit. And the real amazing thing is even within that, with those temperatures, there are new stars that are forming in here. This is a combination image from one of our cameras, near-infrared cameras, as well as our mid-infrared camera. So it looks at a little bit different part of the light spectrum. When you look just with our mid-infrared camera, you get this image on the right. So if you go kind of to the top galaxy, top right, that what looks like a star in the center of it is actually an active black hole. So then with our instruments, we can then do some other cool things with that black hole. We can look at the composition of the gases around that black hole. So you can see things like argon and such coming around that black hole. But we can also measure the velocity of those gases. And they're basically spinning. So as it's coming near you or going away, we can tell. And they're ranging up to plus or minus 200 kilometers per second as the speed at which they're traveling. Exoplanets, I've mentioned before how we do that science with exoplanets. So when that planet gets in front of its star or its sun, we can use Webb to look at the atmosphere around that planet and then begin to determine what elements are in there. The first planet we looked at was about the size of Saturn with the mass of Jupiter. And his sun was about our size, but instead of taking 365 days to go around the sun like we do, it did it in 3 days. But when we measured and took a look at what elements on there, the first thing we found was water vapor on that planet. And that's what this spectrum here on the bottom left is showing us. And that's the signature for water vapor. This is my favorite picture. This is basically a stellar nursery. So inside all these gases, you're finding all sorts of stars being born. It's a very, very cool picture. I forget exactly how far this is away. I think it's 7,600 million light years away. Relatively close in astronomical terms. And then finally, well, actually two things. One, folks say, well, what is it like to Hubble? So on the left-hand side, you have a Hubble image. And it looks pretty cool until you look at the Webb image. And the amount of detail that you can see and the amount of extra stars that you can see is very obvious to the eye of what those differences are between Webb and a Hubble telescope. Finally, this is my own personal favorite because I'm a big Jimmy Buffett fan. He is also a big space fan. And come on. He came to our control center a little over a week ago. So I got to give him a tour of the control center. He was there about an hour and 45 minutes, asked really good questions. But I'd also been communicating with him for a while, and his tech guy. And if you get a chance to see him this summer, I think he had to cancel the Alpine Valley concert a couple of days, or postpone it because of storms. That might be the closest one to here in Wisconsin. His final song is dedicated to the Webb team, and he's using our images as part of his tribute to the Webb team. So I thought that was really cool. And this is the concert he did just outside Baltimore a couple weeks ago. So finally, for my last chart, Hubble, when it first was launched, rewrote the books on astronomy and what we know about the universe. We're going to rewrite them again. It'll be amazing. We're still, we might be out of first gear. We might be in second gear, but we're still learning how to use the telescope. We're going to discover new things that are going to prompt more, hey, let's try this with the telescope. Let's try that. This telescope will be around for a long time. We have over 20 years worth of fuel still on this telescope. We've gotten through the mortality point with all of our instruments. We know they're going to last a long time. So not only are astronomers who are around now going to be able to use it, but probably if you have kids, and they're about the right age, by the time they get out of college and get a chance, if they go into astrophysics, they'll be able to use this telescope. And with that, I think we got some time. We're going to take some questions for a little bit. Thank you.
Let's go ahead and sit down on the left chair.
Yep.
Am I on? Thanks, Bill. That was fascinating, wasn't it? Really, I'm kind of a geek about these things, so I got the privilege of being here with Bill to start out with some easy questions, and then we're going to eventually evolve to the meaning of life, since that's what we're talking about.
Not really.
So first question I wanted to ask, and like I said, these are going to start out pretty easy. How did you know what direction to point the rocket?
That's all determined by the orbit that you want to be in.
Okay.
Through orbit mechanics, you determine which way you want to go, and that gets all programmed into the rocket. So
because we read about this, kind of on a journey back in time, so to speak.
That's not a back in time journey. It's looking
back in time.
Yeah, we were not traveling back in time with the rocket.
So
we're not quite that advanced.
That's what I'm trying to get my arms around. We all grew up watching The Time Machine and Back to the Future and thinking, well, that's what they're doing, but they're not. So you want to just kind of talk through that?
No, I mean, it's like watching any satellite. Let's go Landsat satellite, since we use Landsat here. It has a certain orbit. Those orbit parameters get programmed into the rocket, and the rocket takes you to where it's a truck. Okay. It takes you to where we want to be.
Got it.
It's an expensive truck, but it's a truck.
So on that note, I think it's well documented that it originally was scheduled to launch in 2008 or somewhere thereabouts.
Yeah, it was a lot of different launch dates.
So there were some delays. We all know that. But with delays, is an opportunity for new technology. And so I'm just kind of curious, is there any time from that original launch plan and what we saw this spring where the scientists said, boy, I'm glad we waited because now something new in terms of technology.
No, we didn't make changes. That just adds more risk into the program.
Got it.
We developed 10 new technologies or modified technologies for this program. One being I talked about, well, actually two of them. One, the sunshade. Even though Kapton is not a new technology, the way we used it was new. And the mirrors themselves was new technology.
Okay.
But just because we had problems doesn't mean you have a chance to go in and make changes.
Sure.
As a project manager, that's what I say no. Because that just drives risk, cost, and schedule.
I'm sure people wanted to.
Not really. They wanted to get it launched. So
okay, good. I'm going to kind of bounce back and forth. Does anybody in the audience have any questions they'd like to ask? Matt?
Go ahead.
Yeah, we got up here, Matt.
Matt Paulson, Downtown Rotary. Could you tell us a little bit about JWST's kind of unique orbit? Obviously, it's much further out than Hubble. Why and what's the benefit of that?
Yeah, so it's at a point called the Lagrange point 2. Like I said, it's about 1 million miles from Earth. It's a point where we have a nice balancing gravity between the sun and the Earth pulling us back in and the solar system itself pulling us away. So we kind of stay in that point. It allows us, we orbit the sun at the same rate as the Earth. So it always keeps the sun and the Earth back onto the hot side of the spacecraft. And then allows us to basically have a 180 plus field of view at any time of year. So the advantages of that was easy in that deep field observation. It took us 2 hours to do it versus Hubble. That's low Earth orbit. Every once in orbit, it has to look away because you're going back to the back side of backside of Earth, and then you have to come back around, reacquire the target, and start the observation. So it makes for a much more efficient observatory.
Anything
Next
else?
question.
Oh, sorry. Go ahead.
Yeah, question, Bill Harris. Thank you very much. It's exciting stuff. You said you're looking at infrared so that you can look at further stars, but it
Yes.
still sounds like it's still the same age of the universe that
Yes,
Hubble had,
but
right?
Hubble could not look as far back as we could.
So if you had a better telescope, could you find 20 billion, 40 billion years old? I mean, is it going to get older than? it
The
is now?
scientists, when they take the data from us, may say it's not 13.8, maybe it's 13.9 or whatever. Right now, it's still 13.8. We will be able to look back 13.6. That's our target. After the Big Bang, there was about 200 million years of darkness, and they've derived that from various satellites. And then all of a sudden, the universe started to light up. And so we're looking back to that point when things start lighting up, which is at 13.6 billion. We'll do that probably within the next 6 months. This was, for lack of a better word, playing with the earlier release to demonstrate our capabilities to folks. But the science proposals now we're starting to execute will stare longer at a spot. That deep field image that I showed has thousands of galaxies in it, and I was showing the gravitational lensing that was going on. If you want to understand how big of the sky we were looking at, take a dime, now look at FDR, now look at FDR's eye. The size of that eye is the size of the sky that we were looking at. Now you start thinking about, okay, there's thousands of galaxies there. All galaxies have an average of 100 billion to 200 billion to 300 billion stars in each galaxy. You start doing the math, you get numbers too big that I can say what they are. And then you start thinking about the number of exoplanets that are there. It becomes mind-boggling.
So how about the multiverse? How many universes are we going to find?
Nah, I don't think so. One.
Eric?
Bill, can you still send commands to the telescope?
Oh yeah, we
And
command every day.
how long does it take for them to
Eight-
get there?
8-second turnaround. So it's about 4 seconds each way.
Got one right over here.
I just have a question. How do you stop it from being hit? Is there a chance it could be hit by anything in space?
So you've been reading the articles about micrometeorites?
I have, yes.
Yeah. They exaggerate a lot. So every satellite has to deal with micrometeorites. It doesn't matter whether you're low Earth orbit out there, going to Mars or whatever you're doing. We took that into account in the design of the mirrors. Hence, we have the motors in the back. We can make adjustments if we get hit. At the time, we estimated about one hit a month, which is what we've had. We've had about 5 meteorite hits to begin with. The one that caught attention was the last one hit was a little bit bigger than what we expected. It's not detrimental to the telescope. I'll tell you the truth, all the images I just showed you were taken after that. So you don't see any damage from that at all. We made adjustments. Anytime, any operational project for any mission, we always continue to look at how we operate to maximize to extend the life of the mission. And so we're going through some of that now to look at this. Hey, is there anything we can do to help avoid some of that? You can't avoid them forever because we look away from micrometeorite showers, but there's random micrometeorites, and those are what's caused. That's what we've had so far, random micrometeorites. But what you read in the papers, like I saw one, catastrophic damage to the telescope, and I'm like, not really. So it's just people looking for bad news. That's all it is.
Yeah, as an engineer and a businessman, I'm curious, what kind of an investment has it taken from day one to get
The cost of the mission, it was 9.6 billion over 20 years.
9.6 billion?
Yep. So what I always tell folks is, if you look at NASA's budget with regards to the entire federal budget, we are about 0.1% of the entire federal budget.
So did most of the funding come through NASA?
We funded everything except the contributions from our international partners. And you know what? We've done some over 20 years, what's the average number of taxpayers? And I think it works out to be something like $4 a year per taxpayer as an investment to get something like this.
Anyone else? So just curious, you talked about the specialized material that was used to make the mirrors, but then of course each one is coated with gold. How much gold was used?
The equivalent of about 4 or 5 wedding bands. It's measured in thickness of atoms, not in anything else.
Yeah, so it looks like when you see something that's 21 feet wide, that
Yep.
there's many, many ounces of gold,
Yep.
but they're very
But-
little.
Yeah, we used gold because gold is hypersensitive to the infrared.
Okay. I think an important question to ask also is how many stars and galaxies are on your socks?
No, not quite as many as in the pictures.
Do you have anything else that we'd like to ask Bill? Eric?
Bill, thanks again for being here. Eric Erickson. In the movie Contact, when the first one goes bad, the guy says, why build one when you could build two for twice the price? Was there a contingency plan if the launch didn't go well, or is there a backup plan?
No. No. Talk to your congressman. They wouldn't like us spending another $10 billion on this. We had contingency plans on orbit though. So not for the rocket. The rocket is a truck. You can't, it's a single point failure. And actually we had lots of things. When we launched, we had 344 single point failures. Single point failure means if one thing fails, you lose the mission. By the time we got through deployments, we had narrowed that list down to less than 100. And then there's about 35 that are there for the life of the satellite, but other things like an antenna dies, right? We built up a contingency war chest of about 350 procedures that we could have done in case we had problems with something on orbit. So we were prepared for issues, but we never had to execute any of them.
So you mentioned discovering about Goldilocks planets, and can you talk a little bit more about what the idea is and how many you found or will find, and then what the next steps are to try to look harder, if that's part of the goal, or what the...
I can answer part of your question because I'm not a scientist, so I'll answer the part that I can't answer. We didn't find the Goldilocks planet, the TRAPPIST planets. Any planet that is Earth-like, they use a criteria, will be called a Goldilocks planet. The ones that we looked at first were ones that were well known a couple of years ago, called from the TRAPPIST system. That data should come out, I would say, within the next month, because we just did the observations over the last week or so. As far as next steps, there's a telescope that's being built now that wouldn't really be that next step, called the Nancy Roman Space Telescope. It's actually being built where I work. It's a Hubble-sized mirror. It's usually used to study dark matter. Beyond that, the National Science Foundation came out they come out every 10 years with a recommendation saying this is what NASA should focus on. For astrophysics, it'll be a mission that really looks more towards, hey, can there potentially be alien life on some other planet? The size of the mirror ranges anywhere from the same size we have now, but in a different light spectrum, to a 10-meter mirror up to a 15-meter mirror. All that technology is doable because it's segmented mirrors. It's just more folds. There's talk of building the telescope on orbit. To me, that just adds more complexity and more risk. But if you can get a larger, like Musk's star, whatever, rocket, if that gets working, that could take something like that into orbit. So that's pretty far in the future. It involves, everything from funding to designs and so forth. But what we did right now is we took some of my senior folks who were all within 3 to 5 years of retiring, and we've started a knowledge capture to capture that knowledge and pass on to the next generation, because there's lots of lessons learned that come from this telescope. Trying to pass those lessons learned on. And you don't want the next big telescope to be revolutionary with all this new stuff like we had to be. You want it to evolve from Webb. And by evolving from Webb, that will help you keep the cost down and also get it done faster.
We have time for one more question.
Yeah, you've got many questions, I'm sure, when you go up with the telescope and everything that you want answered. When this first short period here of things that you've seen already, are there new questions that popped up that are enticing you to everybody to dig in further?
The actual first science paper has already been published on Webb, and I haven't read it yet. But just talking to my scientists, which there's a lot more users than just the scientists that work at NASA. They're already starting to get ideas of things that we can do with it further. I got asked earlier, not today, in this group, another group, about how do we select what science gets done. So the science you're seeing right now is called early release observations. They were specifically done with folks from NASA picking out to demonstrate our capabilities, and there's still more coming of each of our different science modes. Then there'll be some called early science release observations. Typical Stellar and Hubble's the same way, and so forth. A scientist and his or her team will propose a series of observations. They get to hold that data proprietary for 6 months, and then it gets made public. Early release science, the data gets made public right away. Then we will jump into our first year of science, real science operations. And there's a call for proposals that go out. Teams propose back. Those proposals get evaluated by, it's like 100 to 150 people, none of which have proposed, so they can't be biased. And evaluate those proposals on scientific merit. And then they get selected for that year of operations. For the first year, there's somewhere around 200, 250 proposals that were selected, but we were over 4 times subscribed. So there wasn't just enough time in the year to do everything that was proposed. So those folks will repropose for the following years. And as I mentioned earlier, this telescope will be going on for a long time.
Great. Bill, thank you. Let's show Bill our warm appreciation for him being here today.
Thank you so much. Thank you.
Thank you. Fascinating stuff.
Thank you.
Thank you.
Kurt, a thanks to you as well. Bill, of all of the words that come to mind, the biggest is congratulations.
Thank you.
That's tremendous.
Thank you.
Next program next week, August 1st, responding to Sioux Falls' child care crisis. Thank you again, everyone, for being here today. Rotary is adjourned.